problem minus for harmonic functions on, say, ball. U in C2 R intersection C0 R minus Laplace of U in side and U equal G. Then where by this we mean the meaning that we give to this the classical meaning. Why? So, and to solve this, which seems very special because it is just for the ball, but actually is fundamental in order to attack the problem for more general open sets, bounded open sets. And the idea was to remember that we had a sort of implicit expression that was the integral y. So we found this expression was called the Poisson kernel. This was called the Green function. Of omega for omega. Green's function was based on solving. So this k is simply minus this normal derivative. So in order to get explicit expression of this kernel, one has to compute this normal derivative. And this gx of omega was based on solving possibly the following. So given x in omega, was based on possibly solving. Now go back to omega equal the ball. The ball, so harmonic function, and Vx equal Gx. Once we know this, then subtracting this solution from Gx, we get Gx omega. Okay, so the problem is now to solve Vx, if possible, for omega equal the ball. And last time we did some, I indicated some, some sort of exercise, maybe. We found, last time we found given in 2 dimensions, r equal 1 and equal 2. Last time we developed this in a series. I think that we were more or less here in the sense that we found we found that the possible harmonic extension was, I think, remember if I use R on rho. So we checked more or less that this was an harmonic function inside, keeping this boundary condition. So for this now, this was harmonic extension. Now we want to try to write this in this form. So this is what? 0 over 2. Then we can, so the coefficients, were 1 over pi minus pi g of pi, an was 1 over pi minus pi cos n was 1 over pi product this I think we were last time. I don't remember if I use R or rho, maybe R. So it seems exactly the same notation. Okay, now so the idea is now to substitute the expression of the coefficients inside here. So try to make some computations and maybe to try to write this u as an integral over the boundary. So the idea now is starting from this expression, try to write u in sort of this form, and then deduce who is this k at least in 2 dimensions and when the radius is 1. So this means that let's try to substitute. So A0 is this. So 1 over 2 pi integral minus pi, the mean value, say, of then r to the n, then we substitute minus pi 1 over pi cosinus pi plus pi integral minus pi and pi now now we can exchange integration by the properties of the convergence of series. We can exchange integration and series here. So exchanging this. So let me write pi. This I copy. The first term just I copy. Then I integral 1 over pi minus pi and pi. We have r to the n. We have cosine theta plus sinus and phi theta pi d phi. So this is, let me write it in another way. Pi between minus pi and pi here. Then I put all together, so 1/2. So this 2 here is just 1/2 now, because pi is outside. Then series, sorry, I forgot to put the series here. Times n. Times n. Okay, so for the moment we have this so this is u r theta. So you see now we are not far from our aim because this is expressed as an integral. So is expressed, and then the minus theta is expressing the integral over the boundary of the unit disk. So there is the integral, but now we maybe have to, and g is also here because u is equal to g on the boundary. So this is okay, this is okay. We have to work more on writing in a different way this kernel. So in order to do that, let's simplify notation. And write theta tilde this difference. So and then let us concentrate with this difficult object. So we work separately on it. So this is this object here now reads as follows: is the series 1 to plus infinity r to the n.
We add imaginary part. After that, it comes from some complex numbers. We add imaginary part for this series.
Yes,
maybe it's useful for.
Yeah, that could be. I want to work only in the reals, but of course one can do all these kind of things using so theta minus pi and
it was just geometric series Zn after adding.
Yeah, let's do this. I can do a small trick now. Theta tilde, sorry. Theta tilde n. Now let us multiply this quantity. Let us multiply this quantity by this. See if this helps. This is a trick. Let's see if it helps. So just instead of computing what is inside this box, I compute a factor multiplied by what it is inside this box. So let's see if it helps. So let's do this. So let's expand now the multiplication, hoping that it works. So what do I get? I get the sum from 1 to plus infinity r to the n cosinus theta plus the sum r to the n plus 2 minus 2 sum r n from 1 to plus infinity r n plus 1 sinus theta tilde n cosine. And I want to try to write this as a I want to, so let me do change of variables here, n plus 2. Plus 1. Like to count. So first of all, I can write this as n plus 2. Let me do a change of variable here, n plus 1, I call it m. So this sum becomes what? This sum becomes sum I'm not so satisfied by this not doing the correct things. I'm not sure. Rn plus 2, it's okay. This seems okay. So maybe let me write it, let me rewrite this sum, I'm not sure. So Rn plus 2 plus Rn cosine theta tilde n. So this is just this. And then there is this minus here. This can be written maybe in a different way. Product, no?
Dividing by 2. We have 2. Yes.
The 2.
Now we have 2 in front of the series, in
Yes,
front of
exactly.
the sigma. So.
Exactly. This should help a little bit. Cosinus n tilde cosinus theta tilde minus this cosinus. So this should be equal to that too, no? Am I right? So this should be equal to minus sum from 1 to plus infinity r to the n plus 1 cosinus theta tilde n plus 1 minus. Okay, this should be, maybe there is a plus, because this is a 2 cosinus without the 2. No. 2 is not present anymore. Now, what do I do? I hope to have several cancellation here. Several cancellations. So let me write this. Now let me split it. Minus sum equal 1 to plus infinity. So I just split theta tilde n plus 1 plus sum n from 1 to plus infinity 1. Now I want to make some cancellation, making change of variables. Let me do a change of variable. Let me call this n plus 1, let me call it m. So for the moment I have this minus this, minus this. So let me call this m, and let me copy this, otherwise I forget. So from 1 to plus infinity, this I copy. Minus, now if I call n plus 1 equal m, that m runs from 2 to plus infinity. 2 plus infinity, r to the m, cos theta tilde m, which should cancel almost all terms of this sum here. Minus. Now let me call n minus 1 equal m here. So what do I get? Minus. Now if n, so this runs from 0 to plus infinity. Becomes n plus 2. Okay. Now there should be several cancellations. In particular, this, starting from 2, this part here starting from 2 is killed by this. So it should remain only the first term here, n equal 1. So n equal 1 means r cos tilde. On the other hand, here, everything here is killed by this, but it remains only m equals 0 here, right? So this gives us minus r squared correct? M equals 0, this is 1, this is r squared with the minus in front, equal 1 r. It seems to me that this is what we get, okay? So what does it mean if the computations are correct? It means that the box, our box, that is part of what we are trying to modify, this box here, equal to this divided by this factor. So this means that the box equal to r cosinus of theta tilde minus r squared divided by 1 plus r squared minus 2. Now I have to check because check if I am correct. Okay, so this now this is just part of our integrand, so now we have to add 1/2. So we can go back to this formula. Can go back to this formula and substitute what we found. So now what I will do, I will substitute this expression inside this box. Okay, so this is 1 over pi, integral minus pi and pi, 1/2 plus r cosinus of theta tilde. Theta tilde, remember, is theta minus phi, minus r squared divided by 1 plus r squared minus 2r cosinus of theta tilde, and this is integrated in d phi. So this seems a kernel. Now somehow it's more similar. These are different variables. These are rectangular variables and not polar coordinates. But so now, hoping that this formula is correct, let me erase something. So let me do just one denominator here. 1 over pi and pi, 2 times 1 plus r squared minus 2r cos theta tilde. And then we have 1 plus r squared minus 2r cos theta tilde minus plus 2r cos theta tilde minus 2r squared g phi d phi. Now so what remains here is 1 minus r squared divided by pi, integral minus pi and pi. Now there is also the 2 is outside. G of phi divided by 1 plus r squared minus 2r cosinus of theta minus. I think that this is an expression in, I think that this is an expression in polar coordinates of our case. So I think that this is what we are looking for. So k in polar coordinates for the ball in 2 dimensions here should be simply 1 minus r squared divided by 2 pi multiplied by 1 plus r squared minus 2r cosinus of this should be written maybe in another system of coordinates. So now maybe this I can leave you as an exercise to rewrite it. So I think this should be correct. If y is on the boundary of the ball, x is in the ball, an exercise to rewrite it other coordinates. So write it well, maybe okay. So y is cos phi phi. X instead is inside. Remember that we are integrating in y, and y is on the boundary, while x is inside. So they are never equal, particular. So we can write y. So remember that g is the value of u on the boundary. So the coordinate, the angular coordinate of y should be phi. The angular coordinate of x should be theta. So x r cos theta r theta. So this becomes, so let's compute now x minus y squared. X minus y squared. This is what is r cos theta comma r sinus of theta minus sinus of phi square. So this is what is r square plus 1 minus 2 r cos theta cos phi which should be exactly equal so what I am saying simply is that finally in this new system of coordinates, rectangular coordinates, k dimensions, ball of radius 1 centered at the origin, equal to 1 minus x squared divided by, there is this 2 pi, there is x minus y. Hope that the constants are correct. So well, we found the expression, at least in this case, no? Agree? Is the computation clear? So we have written u of x exactly in that form, in 2 dimensions on the unit disk, with that choice of k. With that k, we can write this. Okay. This seems correct. We want to generalize this to any dimension, because Of course, here we have used the Fourier transform, which is very, very nice, but it's just only for 2 dimensions at the moment. So it's better to try to do the same computation. So now we do similar computation in n larger or equal than 3. So from now on, this way I also avoid the logarithmic potential. A good exercise could be, so from now on, I fix the dimension of the space. So from now on, I fix the dimension of the space larger or equal than 3. But a good exercise could be, if you have time to do, try to do the following computations, home maybe. The next computation n equal 2. We already know the answer, but and then try to see that these new computations are consistent with what we already know, that we have done in a different way. So we have now the following situation. We have to solve sufficiently smooth Vx, x equal Gx. So, we fix also Br are positive and then Vr centered at 0 for simplicity. If the ball is not centered at 0, then if it's centered at some point P, then for instance here you have here to write x minus P in place of x, okay? But for simplicity now we assume that the origin, we are working at the origin, so I as usual use this notation. So remember we want to do this. So the claim now here, I mean, we are in this situation. We have center, x, y is running around. So y is coordinate symbol for a point on the boundary of Br. X is inside. And we have to imagine, and then we want to find, so given x, we want to find a harmonic function inside which coincides with the fundamental solution having singularity here, fundamental solution having singularity here on the boundary. And the claim is the following. We make a claim which sure that your tutor know infinitely much better than me. Also the reason for doing this. We claim that Vx, so x is fixed, x is inside is fixed. So for the moment x is inside is fixed. Claim that actually Vx is something multiplying G, fundamental solution at another point outside, another point somewhere. For some actually uniquely determined x bar out of the ball, and C is so this is Vx of y, Vx, no Vx, sorry. So where now C is so Vx of y, the claim is the following: C, G of x bar, y, where now we have to determine x bar and C. And C is something which is independent of y at the end. So C is independent, will be, we'll see in the computations, but I anticipate will be independent. So this is just a claim. We look for, let's see, let's put it like this. We look for a possible solution of this problem in this form. Just a claim. We look for Vx, just an attempt for Vx of the following form, of the form Vx equal fundamental solution with a singularity at another point outside that we have to determine. Okay? We don't know if it is possible to find Vx. Of course, Vx, you see, somehow, once x is fixed, if C is independent of, if it depends on x, but depends on x, but independent of y, this will be harmonic, clearly. The problem is that we have this gx bar to have the same value on the boundary as gx here. So we have a singular function centered here with some value on this boundary and another singular function centered outside somewhere that should have the same values on the boundary. And that this can be done is not immediate. Who is x bar? Well, by symmetry seems natural. It seems natural to take x bar along the same line starting from the origin and pass it through x. So some multiple of x for some t will be still independent of y for some t. So now this is just a claim, so let me repeat it. We make an attempt. We look for a solution of this problem in this symmetry of the form some function of x independent of y, g of singular point outside depending on x, the same half line passing through, the same line passing through x. And we have to determine if the claim is correct. We have, of course, to determine the constant, the function c of x and t. If this is possible, then we have found the solution of our problem, because clearly our singular function, the fundamental solution centered at this mysterious point, is harmonic here, because this point is outside. It's not even on the boundary, if you want. So okay. Now, what does it mean imposing this claim? So imposing this claim, so what? What? The x must be, means in particular that on the boundary of BR, that Vx, which must be equal to Gx, therefore it is constant, some constant divided by x minus y to the n minus 2. So this is Vx equal Gx at y. X equal Gx at y, but this is not needed now. In any case, this must be equal to this object here, C, multiplied by the fundamental solution singular at x bar, which is the same constant, Cn, and now it is 1 over x bar minus y to the n minus 2. Remember that if you want to do this kind of computation in 2 dimensions, so we are assuming n larger or equal than 3. But suppose that you want to do the same computation in 2 dimensions, that actually is a good home exercise in order to reach the same conclusion there. You don't have to write this, you have to write the potential, the logarithmic functions, no? Logarithm. So then this doesn't matter. So what is C? C is determined as follows. C is y minus x divided no? Okay. So this is our C. This is our C. For simplicity, now we introduce K. So equivalently, we can look for K. Okay. So for any y, so what kind of, so this must be valid for any y on the boundary of BR. So it seems natural here, we want to impose this constant for any y. If, so in particular, this should be satisfied for this point and this point. So let me call this point y prime, and let me call this point y second. No? For the same, so because we are saying that C is independent of y, no? So I've written here, C will be independent of y. Okay? So if C is independent of y, K is independent of y, and therefore we should have the same K for this choice of y and this other choice of y. So the same K, since we look for a C, look for C independent of y, and for K also. We have the same K, we need same K. If we make the easiest choice possible to go on in the computations, which are this point on the boundary and this other point on the boundary along the same line. So if we choose y equal y prime and y equal y second. Same K. So when we choose y prime, what we get here? So y prime, so this is y minus x. The distance between y minus x is this one, which is r minus the norm of x. No? The numerator is, we get r minus the norm of x divided by y prime minus x prime. Okay, now what is this? It's the distance between x bar and y, but x bar is now, by assumption, we are looking for this x bar, so we have tx, norm of x, minus r. No? So this is our k, but this k must be equal to the, so this k must be equal also to the same k which is coming from the choice of y second. So what's happened if I take y second? So now the distance from y second to x is now the radius plus the norm of x. And then the distance between y second and x bar is the norm of x bar plus r. Okay, so the norm of x bar is tx plus r. Okay, so what these two objects must be equal. So what do I get? Well, I get, imposing equality, I get r minus x divided by tx minus r. This must be equal to r plus x divided by tx plus r. So let's try to expand a little bit this equality. So this multiplied by this must be equal to this multiplied by this. So r minus x multiplied by r plus x. Sorry, no, r minus x multiplied by r plus tx. This must be equal to r plus x multiplied by tx minus r. Okay, so expanding, r square plus trx minus xr minus tx square must be equal to rx minus r square did I write correctly? So r minus x multiplied by r minus x multiplied by r plus tx equal tx minus r. Okay. txr minus r square plus tx square minus rx. Cancellations. This. So we get 2r square equal to tx square. Gives us t equal x square over r square. Okay. So necessarily, notice that when x goes to the boundary, this t becomes 1. No? So this means that x bar, when I'm going to the boundary, tends to x itself. Okay, so this means that essentially when the point is very close, x is here, then x bar is also very close, but on the other side of the ball. Instead, when I go through the origin, x bar is going very far. This seems to be t. The other way around, r square over x square. Yes, thank you. Okay. Now, inserting, what do I do now? I want to find k. Okay, I want to find k. Remember that k is this one, should be this one. Okay, because this is what is this quotient when we take y equal y prime, no? Instead, this is this quotient when we take y equal y second. Okay. So let's insert this t inside this in order to guess what could be k. So k now, just substituting this t inside this gives us what? Gives us r minus x divided by r square divided by x square multiplied by x minus r. Equal to what? R minus x multiplied by x square by r x minus r square. So I can if I'm not wrong, this seems to be, now we should check. Square minus rx. So it seems to be x divided by r. Divided by r. Is it correct? Correct.
Yes.
Yes, is it correct?
Yes.
Okay. This means that our C is k elevated to the n minus 2. So at the end of this sort of guess, which is not a proof, just a guess for the moment, we deduce that if the claim is correct, necessarily t must be r squared divided by x squared, x bar is tx, and where is it? K is equal to x over r, and therefore C is x over r to the n. Now I would like to check, because I would like to check the expression of k. Oh, I made a mistake. It seems that k is r over x again. R over x, not x over r. Why? Why I made a mistake here? I inverted this R over X. So maybe I made a mistake here. K was 1 minus X. Because what did I do? Because I notes it's here I know I called the C and 1 over C. Okay. Cx bar C divided by yes, because it was in the first step, no? It was in the first step. So C is this divided by this and not the complement. So from this we get, this. Okay. Small modification. This leads us to this small modification. I called C a 1 over C. So this is actually R over X divided by n minus 2. So, as you see, what we have proven almost nothing, in the sense that if the claim is correct, then necessarily T must be this must be a famous expression, R squared times X, and C must be this. And we can check T is independent of Y, C is independent of Y, but depends also on depends on X and the dimension. Okay. Now. Well, this is a guess. So, in order to be sure that what we are doing leads to something interesting, we have to show that now, with this choice, the only possible choice in order the guess to be true are those, because they must be true, valid for any y, and we choose a special y prime and y second. And now we have to show that for any y, we have this equality. If we show that now for any y, with that choice of t and k, so it remains to show the following, that for any y on the boundary, this choice, that the only possible choice 1 and 2, 1, 2, and 2, we have that our equation. So C equal this divided by this. So equal equal. Well, let me write. So K was that. Let me start from this. K square equal this square divided by this square. Okay, is equivalent. Otherwise, I have K square equal y minus x squared divided by y minus x. Okay, so this clearly, so it's better to take the squares because we can expand. So k squared must be this divided by this square, which means that we have to check that k squared multiplied by square multiplied by y minus x square, we have to check if it is true or not that it is equal to this. What does it mean? With our specific choice, k was this. So this means x squared. So let me substitute k. X squared divided by r squared multiplied by y minus x squared. We ask if it is true or not that for any y on the boundary, this is equal to y minus r squared over x squared multiplied by x squared. So this is our problem. Okay, this is our problem. Have you understood the strategy of the proof? Make a claim. If the claim is correct, we impose it for two special choices of y. This gives us expressions of k and t that, since they are independent of y, so we get k and t. And now these are the only possible choice of k and t, but this we have to check that now the equation is valid for any y on the boundary, not only for y equal y prime and y second, but for all other y's. The more strange y here. Okay, so now we have to check this formula. Let's try to expand it. Yes. Okay, so we have the square of the norm, so we have scalar products. So x squared over r squared. The left-hand side is what? Left-hand side is x squared over r squared times y squared plus x squared. This is the left-hand side times y squared plus x squared minus 2xy. The left-hand side. The right-hand side instead is y squared plus r to the 4 x to the 4 4x squared minus 2r squared divided by x squared. If I make mistakes, please stop immediately, because you see, otherwise I go on x scalar product with y. Okay, so this right-hand side is also equal to y. We are on the boundary, so this is r squared. Y is on the boundary. This is r4 divided by x squared. To r squared divided by x squared, x y. While this is what, they do not seem really exactly equal, unfortunately. I made some mistake again. So what did I do? Correct, no? I didn't change y, this y minus x squared equal y minus x squared, that's correct, equal y minus y minus x bar squared equal k squared y minus x squared. Go on.
Excuse me.
No? K squared, if I'm not wrong, k squared was, let me, did I do it correctly? K squared was, k squared was r over x, not x over r, apparently. Because again, no? Here you notice that this was r over x, but also k is r over x. So same mistake. Because I corrected c, but I didn't correct k. No? So this means that this is not x over r, but it's r over x. Okay. Now I hope that it should work. Sorry, I corrected this, but I forgot to correct this. So let's go back to this. So this left-hand side now changes, and we have r squared over x squared. So now we can go on. This becomes, so this becomes what? Now remember, this is r squared, so this is r to the 4 x squared plus r squared minus 2 r squared divided by x squared x. Okay, and they are equal. So they are equal, and we are happy. Modulo some mistake of exchanging numerator and denominator. So this means that our problem has a solution, and our solution has this expression. Okay, so this is Vx. Okay, so the problem, they are equal. So for any y, we have found our claim was correct. Correct. Okay, so now let me give you some exercise, maybe. So home. So remember that we have to, so we are interested in the green function for the ball. Well, remember by definition was this, our definition. So this means that this becomes gx minus, let me substitute star inside that formula, c x bar, where c is defined there, and x bar also. Okay, home, show, so where? Here. Depends on x and dimension, and x bar depends on x, but they are both independent of y. Okay. Okay, show that the following expression holds. So when omega is the ball, so gx br centered at the origin, right? Is equal to some constant. This is the same constant appearing in the fundamental solution. So this is not surprising. But more interestingly, we have this 1 divided by y minus x to the n minus 2 minus x squared y squared divided by r squared minus 2 scalar product x with y plus r squared. Check. 2 square. So of course you have, this is just a computation, no? So what you have to do is, this is gx, and then you have to rewrite this gx bar using, not be so difficult, no? So I think this you can do for any x in BR. Where is y now? Well, y is the argument of Vx in some sense, so surely y must be on the boundary, but Vx is defined also inside. So for any y on the boundary or inside, of course, there is a singularity when y is equal to x, no? So this expression is well defined only when y is different from x. We don't need to extend outside, we could, but we think we don't need to think about y outside. Okay, so this is the Green's function. This is finally the Green's function for the ball of radius r centered at the origin, which is, and now the second exercise, that once you know this, you can compute the normal derivative of this minus the normal derivative of this function on the boundary, no? So the second exercise, so home 1, this is a computation. Home 2, finally answers to our initial original question to compute the Poisson kernel for the ball. And the home 2 exercise, so k of the ball, xy that I recall you is minus the normal derivative this is just this is equal to well, it is equal to something very similar to this. So there is here this prefactor must change and must depend on r, but this is similar. So also the power is n. So is equal to the constant is 1 sigma n minus 1 r 1 minus x squared divided by x minus y to the n. No, there is a mistake. This is not 1, is r squared. Okay. So what matters here again is the power. Is this power here? This is fundamental so check. So this is a second exercise. So you simply I mean, and this for which y? For any x on BR, for any y on the boundary, because now we are really working on the boundary. Because y is on the boundary, because we are taking the normal derivative on the boundary, so y must be on the boundary. Okay. Let's see, is this consistent with our Fourier computations? To be consistent with what we found with n equal to 2. Well, there the radius was 1, r squared, this is there, power is 2 dimension, it is there. The problem is the constant, r is 1, so sigma n minus 1 yes, sigma n minus 1 is 2 pi. No? Sigma n minus 1 is the length of the unit circle. So the formula is consistent. It's exactly the same. So we get the previous formula. So this is the same formula, but in any dimension, n larger or equal than 2. Now, difficult to remember this singular kernel here is difficult to remember, but at least one thing we can remember. So if you want now, finally, we can write, supposing that you have done this exercise, finally, we can write, we can make a conjecture if you want. The conjecture is that following theorem that we have to prove, nice theorem, finally an existence theorem, but something more because it is an existence, uniqueness and representation theorem. Everything all together. So let G be continuous, prescribed, then the unique solution, this we have to prove, maybe not today, but solution to our Dirichlet problem minus u in 2 BR intersection C0 BR bar minus Laplace of u equals 0 in BR limit x goes to y of u xy equal g of y for any y is u of x g of y okay, this is the final, our first, once we have done all these computations, I think this you have to, I mean, we have to be, we agree in some sense that this is a reasonable possibility of being a solution, no? Because this is nothing but, this is k of the ball. So this is nothing but k of the ball, g of y. Okay? Yes, this is the reasonable conjecture. So the unique classical, so the unique solution in the classical sense, in the most classical sense of our problem with a continuous boundary condition of on a very, very smooth bounded domain, the ball, is this. Okay? This we have to prove, even if we believe to be true. There will be just only the problem that we are keeping correctly the boundary condition, but more or less this is reasonable. Okay. Okay. One remark. One remark from exercise 1. There is an interesting fact here. So here x is in omega and y is in omega bar, okay? In particular, also y is in omega. we could also, okay, now this, we have gx, this remark, was not, I mean, not so immediate from the beginning, no? Because this is, looking at this, it was not so immediate. So the remark is that gx bry is equal to gy brx for any x and y in Br. So we have symmetry. Okay. So before concluding, I want to leave you another exercise. But so the exercise 1 is a computation, and exercise 2 also is a computation. Okay. So maybe doable, not impossible. And now I'll leave you home exercise 3. Home 3. Is a list quite immediate, I would say, from the definitions, but let me point out. So, given x, now omega is the ball, function y into y is harmonic. Omega minus x 1 y in omega, the function y, uh, 3, given y omega, function x associating the gradient now this is a vector valued function, so all components is harmonic in omega minus y, in the sense that all components of the gradient are harmonic. 4 is more difficult. So these are, I would say, immediate. This is immediate, somehow, by construction. No? Because it's just a difference of an harmonic function minus another harmonic. So this is point 2, maybe not so immediate, but becomes immediate once we have exercise 1, which shows symmetry. Because exercise 1 shows that you can exchange x and y, and nothing changes here. So, because this is symmetric, this is symmetric, this is symmetric, and nothing changes. So, exercise point 2 follows from point 1 and the symmetry. This is somehow a consequence of the fact that we know that if you have an harmonic function, their derivatives are harmonic. So this is less than the fourth exercise is then harmonic. More difficult. So these are the exercises. Okay. tool for finding some harmonicity of the. Okay, so thanks. Time is over, I think, and we will meet tomorrow. Bye-bye.
Thank you.